Okay, so we have provided with the introduction about what are the artificial neurons we can use for building deep learning models. And next, we'll introduce our first deep learning model. It's called a multi-layer perception for you. And for the multi-layer perception, it improves the classic perception model with more hidden layers to make this model architecture much more deeper, right? And in the following pages, we will show you what are the hidden layers and what are the multi-layer perception models we can use or we can build, utilizing these neurons. So in the previous pages, we will provide you with history about deep learning development in the past years. We mentioned that since the proposal of the perception model, then Minsky's textbook actually, generally killed this area, right? Because it points out that the perception cannot even handle a very simple nonlinear separation task. And you may wonder what is happening in these years and what is the nonlinear separation task mentioned by Minsky in his textbook. And so let's talk about the perception model first, as well as its weakness as proposed by Minsky. So for the perception model, its architecture is very simple. We have the input layer and we have the output layer. As shown here, given the input layer, let's assume we have two inputs only, x1 and x2. We have two inputs, and this input will be from the data inputs, right? We have the data sets. And between the input layers and output layers, we have the weights connecting them, denoting the weights, right? Denoted by W1 and W2. And we also have this output Y, right? According as defined by the neuron we defined before. Given the inputs, the weight, as of course the threshold by the neuron, we can generate its output, right? So here we can use a very simple activation function. For example, if we have the input larger than 0, the activation function will return 1, otherwise it will return 0 instead. Let's assume we utilize this step function as activation function for the neuron here. Okay, so given the input, the weight, as well as threshold, and the activation function, we can define a perception model as shown here, right? Then, as pointed out by Minsky in his textbook, he proposed a very simple toy dataset. The toy dataset is defined by the XOR as operator. So according to the XOR operator, we can generate a very simple toy dataset with only 4 data instances. So if you still remember this logic operator XOR, right, given two inputs, if the inputs are the same, it will return 0. If the inputs are different, it will return 1, right, for this XOR operator. So according to this operator, we can generate the data set like this. We have two inputs, we have one output. And given two inputs, if we have the inputs to be 0, 0, we will have 0 to be output, right? If we have 0, 1, its output will be 1. If we have 1, 0, its output will be 1. And if we have 1, 1, its output will be 0 instead, right? This is a toy dataset with only 4 instances, with 2 features, and with 1 output, right? And if we try to learn a perception model with this toy dataset, we find that no matter how we train this model, we can never train a model to fit this dataset. The main reason is because if we draw the dataset, the distribution in the feature space, we find that actually this dataset defines a case that linear models can never separate them. So if we project the dataset into the feature space, we find that we will have 4 dots, right? And we have 2 plus here denoting the positive instance, and we have 2 negative mark denoting the 0 label instances. Since this perception defines a linear model, in other words, we can only draw one single line to separate the data instances. You will find that no matter how we draw this line, we can never do a correct classification for this task, right? Because if we draw one single line, we can never separate them into 2 classes. We will always make one mistake, right? No matter how we draw this kind of lines. So according to Minsky, this perception model cannot even handle a very simple case like this XOR dataset. Then how can you say the perception model can handle more complex real-world application datasets instead, right? So due to this kind of example, this example generally killed the perception as well as neural networks for more than 10 years. It's toy datasets, right? Okay, so this is the perception model and its weakness as pointed out by Minsky. And after that, people don't do research in this domain generally for more than 10 years until some people propose we can utilize some of the hidden layers to add more layers into the perception. What does this mean? So besides the input layer as well as the output layer, we can add some more layers in connecting them. We define this layer to be the hidden layers. So given the inputs x1, x2, we added some more neurons, like C neuron, D neuron there, right? And this neuron will be just like the neuron we defined before. It has inputs with some weights, also have some threshold, also the activation functions, right? So if we add some hidden layers into the perception model, then we will be able to handle this nonlinear separation task very easily. So given the inputs x1 and x2, we can define a multi-layer perception model with one hidden layer, and we also define the weights we can assign to them as well as threshold to them. Like for example, if we assign this weight to be positive 1, this one to be negative 1, this positive 1, this negative 1, and we also define these two weights to be positive 1, and we assign all the threshold to be 0.5, then we can find a very trivial solution of trivial model architecture, which can correctly classify all its instances in the XOR dataset. So compared with the classic perception with just input and output layers, this one has one more layer. It's called hidden layer. Therefore, we can name this kind of model as a multi-layer perception, or MLP for short. So besides one single layer, you can also add more hidden layers inside it. You can have multiple layers, hidden layers inside this MLP as well, right? Depending on your task as well as the data input. So you can see in this way we can address its kind of a toy data set as pointed out by Minsky very well by including the hidden layers. So this multi-layer perception can not only address this toy data set, we can also utilize this multi-layer perception to do many of the real-world application tasks as well for the image classifications. So normally if we have some image inputs, if you know, right, this image can be represented as a matrix, right? This matrix inside will have like RGB. In other words, if this image is a color image, we will represent this image as a tensor with three matrix, right? One matrix denoting this red, one matrix denoting this green, and one matrix denoting this blue, right? With this three-channel matrix, we can represent this color image. So here, if we plan to do the classification of these images by utilizing this MLP model, we can also do so, right? So given the image, we can convert it to a three-channel matrix first. Then we can do the matrix to vector and do the reshaping, right? We can convert this matrix into one vector instead, with some entries denoting red, with some entry denoting green, and with some entry denoting blue, right? We can always transform this image into an ordered vector instead, right? Then we can feed this vector as inputs for the multi-layer perception. Now as shown here at the bottom, right? So we have input layers. We literally receive inputs from the images, for this vector. And for the image classification, this task will be more complicated, right? Normally we can have multiple hidden layers. This one will only have one single hidden layer, and for the image classification, it will have multiple hidden layers. So for your stage 2 project, you also have to build a multi-layer perception model. For the toy data set we show in the stage 1, we build a MLP with one single hidden layer. Then for your stage 2, you probably have to incorporate more hidden layers in the model architecture to see which one can achieve better performance, right? So by feeding these vector inputs as a vector to the MLP model, and we also incorporate more hidden layers inside it, then we can generate this output, right? And we can do the classification of this image. So this will be the application of MLP for the image classification in the real-world datasets. It can incorporate more hidden layers inside it. However, the general architecture will stay the same, similar to this one, right? So by incorporating the hidden layers, we can address many of the nonlinear separation tasks for the model very well. And then you may also wonder, how can we train an MLP model? So first of all, we need to define some terms before we introduce this algorithm for training the MLP model. So we use some terms here to define the MLP model. let's assume we have the input layer, and here we assume we have one single hidden layer, and we also have one output layer. So for the inputs, we denote these inputs by x1 until xd. It's denoting the dimension of the inputs. And we have y1 hat denoting the prediction output by the model. We have y1 until yl, l denoting the output layer dimension. Between them, we have the hidden layer. We have b1 until bq. We denoting this q by the dimension of the hidden layer of this vector. And the output will be b1, b2, and b until bq. So for the neurons, we have the weights as well as threshold, right? So for the hidden neurons, in the hidden layers, we assume their weights connected to the inputs denoted by the V1H between X1 and BH, these two neurons. And similarly, the weight between the XD, this neuron, with this BH neuron is denoted by this VDH instead. And for the hidden neuron, we denoted its threshold by gamma H here. Okay, so this is for the hidden neurons. Then for the output layers, these neurons, we denote its connection weight with hidden layers by W instead. For example, the weight between the B1 neuron with YJ, this neuron, the weight is W1J. Similar for the remaining ones, right? And I will also denote the threshold by theta J, as shown here. We provide them with different notations here just to differentiate which one we are talking about and how we do the learning for them. So according to the inputs and the notation we show here, we can calculate the intermediate results of both the neurons in hidden layers as well as neurons in output layers, right? So according to the neuron we defined before, the artificial neurons, right, given the inputs, so when we are calculating the BH, this hidden representation, for example, right? So when we are calculating the output for this neuron, how can we calculate it? Given the inputs x1, xd, and with the weights v1h until vdh, right? So we can first calculate their weight summation, right? And we can define intermediate result to be alpha h for this neuron. And further considering its threshold as well as activation function, we can represent the output by the hidden neuron to be BH equals to F alpha H minus gamma H, right? This is a weighted summation, this one denoting the threshold for the neuron. In this way, we can represent this output for the hidden neuron, right? So based on the hidden neuron, we can further define how can we represent the output neurons. We just show you the representation for the output neuron YJ hat here. Similarly, given the hidden neuron outputs B1 to BQ, we can calculate it in a similar way like this one, right? According to the inputs. Given this representation for the hidden neurons B1 to BQ, we can first calculate the summation of them and weighted by this W weights as shown here, right? And we can denote this weighted summation for all the hidden neurons to this YJ, this neuron, as beta J. This beta J is an intermediate result, right? It denotes the weighted summation among all the hidden neurons. And here for this YJ, the neuron will have the threshold to be theta J, and then we can further represent its output YJ hat equals to F beta J minus theta J, right? So by these two formulas, we can generally represent all the hidden neuron outputs as well as the output neuron outputs, right? By these two formulas. Here, let's assume if we are doing the training of this MyMLP given a data set. Given a data set, we have the data instances, with both the feature inputs as well as ground truths. Here, this xi denoting one feature vector for the i's data instance. This I is different from this I here, right? We should avoid this kinds of confusion here. This y denoting this ground truth. And then, according to the model architecture as well as the formulas we show above, right, we can calculate all the y's by the model for this data input. And we can represent this prediction results by the model for this data input as this y hat, right? And we can further define the loss function for this data instance. Here we use the square arrow as loss function, right? We can compare the ground truth vector versus the prediction vector by the model. And we can sum the squares of differences together to define loss term for this data instance. Then the question will be, how can we train this model? We have learned this gradient descent algorithm before, right? Can we directly use this gradient descent algorithm to help train the model, or do we have any better options? And we'll discuss it later in the following pages.